Hey students, Jock here. I'm going to remind you or teach you about three very important ideas you need for a new topic: voltage, current, resistance. My first video ended up being really shaky, so I'm doing a computer to make sure. Here's a simple situation. Battery powering a light bulb. You hook up two wires, one from the positive end to part of the light bulb, and then one from the light bulb, another part, to negative end of the battery. Electricity flows, turning it on. This is how we're going to learn about it. But we can also draw a simpler picture. This right here is the battery. This right here is the bulb. These are the two wires. Here's another picture, kind of similar. You can see there's two sets here, which means there's probably two batteries hooked up to give you extra strength, one after another. This jagged line could also stand for a bulb. We're going to call it resistance eventually, and it's got a certain unit. So both these pictures and this all are the same thing. So I take pictures like this and I turn it into simpler schematics. Now I want you to understand this is a closed system. Electrons are being pushed through the wire, then pushed through the filament of the bulb. That filament gets hot, gives off light. It does not actually give off electrons, so the electrons stay in the system. So if 100 electrons leave this end, 100 must eventually end up in this end. Now for the story, it's like saying things start at the positive, go through the bulb into the negative end. In physics, we're going to say it's to start off at the high voltage end, aka positive, go through the resistor, aka bulb, and to the low voltage end, also known as the negative end. I want you to imagine a dam, for example. Water starts off high and then falls down because of gravity, goes through the turbine, and ends up low. High height to the turbine to low height. The turbine spins around and makes electricity, but the turbine doesn't actually take water out of the system. It just simply uses it to make something happen. Electrons don't leave the system. They're simply used by the resistor to make something happen. Now, imagine if you have if you have a turbine between two equally high sets of water. If water doesn't fall, it's not going to turn. So you don't get any energy out of it. Just like if both these things have the same V, as we're going to say, nothing's going to flow. So to give you the sense, the battery is the thing that make the push. It pushes charge to flow from one into another. It has a high point and a low point. We're to call that idea voltage. That's that V. I also call it electric potential. I'll call it EMF. All things mean the same. So our story has the positive end to the negative end. We're going to say it's from high voltage to low voltage, or it's from high potential to low potential, or it's from high EMF to low EMF. Electricity actually flowed from one potential to another. We're to call that the current. Just like water, the current flows from high to low. And finally, the bulb itself restricted the flow. It turned energy into light, and we're to call that its resistance. Kind of like rapids or the turbine in a way. So when it comes to voltage, it's measured in volts, and it's simple as V. It's the kind of the push of the electrons. And just like with height, you need a difference in voltage for electricity flow. If you try to connect two ends of a wire and both those ends have the same voltage, a light bulb won't turn on. You need to have one high and one low relative to each other. Other words again are EMF, electric potential. So looking back here, for example, if this was 1,000,000 volts and this was 1,000,001 volts, electricity would flow the other way, and its effective voltage would be 1 volt. If this was 3 volts and 1 volt, the effective voltage would be 2 volts, which means it'd probably have more flow than the other case. Even though it's going from 1,000,000 to 1,000,001, it has less voltage difference than from 3 to 0 or from 4 to 1 or whatever. So long story short, what matters is how much difference there is. So take an average outlet in America. The voltage is 120. That means of the two prongs you must hook up, they must have a difference of 120. It doesn't matter if it's 240, 120, 121 to 1, or whatever. You can't have a negative voltage. The lowest voltage, which is called ground, is 0. So if you just plug something into one prong of an outlet, it won't work, because there won't be a difference in voltage. And of course, what flows? Electricity. Electricity flows on a wire. What's actually happening is the electrons are jumping from atom to atom. And in doing so, they push another one out. So when this one jumps to this atom, it pushes the electron from this atom over to this one, and it kind of travels down the line. It's very fast. It's not like one electron's immediately just jumping across the way. It's just that it's kind of like, again, ripples of water. The first atom of water pushes the next atom, and next thing you know, you have a flow. And that's what current is, the flow of electricity. Current's, we're going to call the letter I. It's measured in amps. And again, by definition, it flows from high voltage to low voltage, just like water, by definition, flows from high height to low height. Current is charge over time, and charge is in coulombs, so amps are coulombs over seconds. This is a pretty important equation to figure out how much charge flowed in some amount of time. Then finally, you have resistance. Once again, voltage was kind of like the height, and it's the push. Current is the flow, what moved. Resistance is what kind of makes it not move all at once. It's the object's resistance to electrons flowing, and electricity gives off heat. Think of it as kind of like the size of the river, also kind of like the rapids in the river. Resistance letter is R, and it's measured in ohms, which is this lowercase omega. Remember, even though there's resistance, electrons are never lost. It's just some of the energy. So if you have a wire, again, think of this like a river. These are the banks of the river. The water flows through here. 4 things affect how much water can flow. The first thing affects is the length. The longer the wire, actually the more resistance, which means there's less flow. So if you want something to flow quickly, you want to have it really short. The longer the river, usually the less flow per unit length. The longer the wire, the less flow per unit length. The thicker the wire, the less resistance, there's more flow. So if you have a long wire, you have less flow. You have a thick wire, you have more flow. Material. You could probably imagine the more conductive or the more metallic it is, the better it flows. Making a wire out of hair, not much flow. Also really smelly. And finally, temperature. The hotter it is, the less flow. So the hotter it is, the more resistance there is. Here's a picture I want you to understand. Voltage is the push. Amps is what moves. Ohms tries to stop it, and doing so gives off energy. Notice how the voltage is only one side, because this is the voltage difference. If both sides of this wire were the same voltage, you'd have equal pushes, no net force, and no net movement, so no current. So again, current is the flow of charge, from high to low, resistance versus against it. And once again, because people like to do anime of this stuff, I guess, here is the story. Voltage is the push. Amps is what moves. Resistance tries to stop it, also kind of harnesses it. So, we got to talk about ohmic versus non-ohmic. If something is ohmic, that means the resistance doesn't change. Which means if you have a wire, it's not going to suddenly get thicker, it's not going to get longer, it's not going to change material. But the one thing that usually does change is temperature. So because of that, we say an ohmic situation is when temperature doesn't play a role. This equation we'll talk about in a second. If it's non-ohmic, that means that usually something's getting hotter or colder, and in doing so, the resistance does change. So if something is ohmic, and let's say you pump electricity through it, an hour later it'll have the same number of ohms. Let's say you double the push, you'll have double the flow. The resistance won't change. If it's non-ohmic, however, that's not the case. An hour from now, it may have much different resistance, so much different flow. If you double the resistance, maybe the flow won't double. Maybe the push will change, I don't know. So in summary, ohmic situations means temperature is constant, so resistance is fixed. As you increase the voltage, you increase the flow. This is called Ohm's law, V equals IR. But notice that delta, because it's not the voltage, it's the voltage difference. So push equals flow times resistance. If you were to graph it, if you double the push, you get double the flow. That's a linear slope, and that's resistance. Non-ohmic means temperature does change. So this does not work anymore. You can't use this relationship, because this only works for a given point. But if you start doubling the push, maybe the flow will triple, or maybe only go to 1.5, maybe even go down a little bit. You never know. So for an example, which of the following could you do in a light bulb situation to always bring about an increase in current? All right, if you increase the push, increase resistance. Will that always increase the current? No way. You could increase the push a little and increase resistance a lot, and the current will overall go down. Decrease voltage, decrease resistance. Again, that probably doesn't work. Less push, but less resistance. It could work, but it doesn't always work. So it has to be C. You must increase the push and decrease the resistance. That is guaranteed to make it more flow. So right now you should learn about the flow, the push, and the resistance. I did a little example here just to kind of show you what I'm talking about mathematics. A battery has one end being 20 volt potential and the other end is 12 volt potential. First of all, find the effective EMF, aka the difference. Well, 20 and 12 gives you a change in voltage of 8 volts. That's how much you actually have to work with. That's the height difference. That's the voltage difference. Find the current flow of ohmic. Okay, V equals IR, but I don't know R, which makes sense. I had to hook this up to something. If I don't hook it up, then it's going to flow. So I need to hook it up. Let's say I hook it up to a 2 ohm wire. I could find the current from V equals IR and get 4 amps. Obviously, if I change the resistance of the wire, this flow is going to change. And in 10 seconds, how much charge flowed? Well, I equals Q over T. Solve for Q, you get 40 coulombs. We're going to take this and go beyond, but you have to understand these 3 major ideas. Thank you and have a good day.